Okay. So first is odds ratio. Uh, Odds ratio is, of course, in ratio measure, right? Odds ratio interpretation, remember that, only applies to a logit model only. It does not apply to either a problem model or a third kind of binary regression model that I um, uh, have not covered yet. It's called C-log-log model, which I don't think we have time to get into details. So for the logit model, we have the probability set up like that, right? For example, for y equal to 1, the probability equal to the natural exponential of x beta over 1 plus the natural exponential of x beta. Okay? And with very simple algebraic rearrangement, okay, we can express x beta in terms of probability, okay, like that. Okay? So first equation here is to express probability in terms of x beta. So is exponential function of x beta over 1 plus exponential of x beta. If you reverse this process, that is, you figure out x beta in terms of probability, then it's log of probability of y equal to 1 over 1 minus the probability y equal to 1. And in the denominator, actually, it's what? The probability y equal to 0. And that is basically odds within the parentheses if you've read the literature or textbook closely enough, right? So here, the odds, that is omega, is this term. Okay, we use this omega sign in Greek alphabet system to denote this odds. Okay, so log of odds equal to x beta. Also, we have this computational form for probability here, right? In this form, we're going to compute this exponential function twice, right? And in old days, that's going to take, well, twice the time, right? And today, to run a logit problem model, it's going to take just 100 seconds, right? But in the past, when computing power is still limited, sometimes we figure out a computational formula to make computation less time consuming. So we can go through this process and get this result. Basically, we divide both numerator and denominator by the natural exponential function of x beta, and we get last term, that is computational formula for the probability of y equal to 1. That's 1 over 1 plus exponential of negative x beta. Okay, and we're going to move on, right? So from here, right, log of omega equal to x beta. What we're going to do next? Well, we can take exponential of both sides, natural exponential function of both sides, and we will get this. Remember that log of omega, right, is equal to x beta. And then we take exponential function of both sides. Note that the natural exponential function is a inverse function of log. Basically, that means they cancel out each other. So once we do that, we will get this. And let's assume we have one intercept and 3 covariates or 3 predictors, right? It's going to be expressed like that. And let's focus on, and from here, right? If you review our math basics documents in the first week, right? From here, the second equation, we can get to the third equation. Okay? So that's one property of the natural exponential function. And so that's pretty straightforward. And let's focus on x2. So what I'm going to do is I'm going to increase x2 by 1 unit. Okay, fair enough? increase x2 by 1 unit. So if I increase x2 by 1 unit, right, this term going to become that term, right? I simply increase x2 by 1 unit. And then we expand that term using distributive law, right? So this, it's going to become 2 terms, right? So the exponential of beta 2 multiplied by x2 plus 1, everything else stays the same. But that term, once we apply the distributive law and also the property of natural exponential function, we will get the second term. Let's focus on the part that's on the line highlighted on the line in red. Okay, right? So from here to here becomes 2 terms, right? And what we're going to do is we're going to take a ratio of these 2 odds. So this is odds, right? So odds is the probability y equal to 1 over 1 minus the probability y equal to 1. Now, actually is equal to what? The probability y equal to 0. And this is quite often used in gambling, if you know this term, odds. If you don't know, check out either my lecture notes, basics of math for CDA, my document, or our textbook. Okay, so after we take the ratio of these 2 odds, right, what we'll get? Well, the only term that's added to this new odds after we increase x2 by 1 unit, right? A generic variable. It does not have to be x2, but it could be x1 or x3. Okay? And here, it does not have to be 3 variables, covariates. It could be 10 or 100, right? It could be a large number of covariates. Well, the only term that's added to the second odds is what? Is this additional e raised to power beta 2, right? The exponential natural exponential beta 2. And after we take ratio of these 2 odds, right? Remember that the start odds is we don't know, where x1, x2, x3 is. We just say, well, let's take that, some unknown but fixed x vector as a starting point, and let's just increase x2. So in the numerator, increase x2 by 1 unit, and then take a ratio of these 2. What is the outcome? Well, that is a constant that does not involve any x values. So this is the beauty of using odds ratio coefficients. So basically, after estimation, we will get beta, right? It's called beta what? ML, right? In previous sections, we talked about how to derive beta hat ML, right? Maximum likelihood estimator. Okay. So once we get that, we take the natural exponential function, then we get what? What is called odds ratio coefficient. Okay. And we take a ratio of these 2. Right here, I'm just using generic variable. We get the natural exponential of beta. And that can provide a very nice interpretation for the effective, x variable or explanatory variables. In this case, actually x2. So in this case, we're going to say for each unit increase in x2, okay, we would expect the odds of y equal to 1. Because that's how odds is defined, right? The odds is the probability y equal to 1 over 1 minus the probability, right? Y equal to 1. Okay? That is odds. That is how odds define. And check that out in our math document, right? That very simple and short review of math, basic math facts, right? So we're going to say odds is going to here. Well, Increase or decrease, we don't know. Okay, that really depends on the value of the natural exponential function of beta 2. Okay, but we're going to say, well, the odds of y equal to 1 going to vary by e raised to the power of beta 2, that amount. So here, the effect is multiplicative. Okay, it's not additive. It is multiplicative. Okay, it's increased by a factor of that amount. So let me repeat. Okay, so for each unit increase in x2, we would expect the odds of y equal to 1. Here we don't know, what y equal to 1. In empirical examples, you're going to clearly state what y equal to 1 stands for. Okay, so here we're going to say, well, for each unit increase in x2, we would expect the odds of y equal to 1 vary by a factor of e raised to the power of beta 2, holding all other variables constant. So here we can make a very, very nice statement. Here we can say, well, it doesn't matter actually what values all other explanatory variables are held to. It doesn't matter, okay? And it doesn't matter even for x2, where x2 starts, okay? As long as we increase x2 by 1 unit, okay, we would expect the odds of y equal to 1 vary by a factor of e raised to the power of beta 2. Okay, and we can use different ways actually to interpret that odds ratio coefficient. A lot of times we use factor change. So we say, well, for a unit change in xk, okay, here I use a generic variable xk, the odds are expected change by a factor of e raised to the power of beta k, right? Again, for generic variable xk, holding all other variables constant. And here we have 3 ways to see that. Well, net of the effects of all other variables or all other explanatory variables, or ceteris paribus, okay? Ceteris paribus. So that's a Latin way to say, taking out of the effects of all other variables. If the value of exponential function beta k greater than 1, we could say that the odds are that amount times larger. Okay, so if it is 1.5, let's say, then we can say 1.5 times greater or larger. Sometimes it can cause confusion. So when that happens, you can say, well, the odds is going to increase. At least we know it's increased by a factor of 1.5, as opposed to saying times larger. When we say 1.5 times larger, sometimes people get confused because they don't know whether that's a factor, increased by 2.5 a factor or 1.5. Okay, and when the exponential natural exponential beta k is smaller than 1, then we can say, well, the odds decreases by a factor of that amount. So we don't have to say how many times smaller, because sometimes people get confused. Okay, and here there are some interpretations for standardized change, and I'm not going to get into such details, and you can look at my notes, but in my lecture I tend to minimize my discussion of standardized coefficients because of the concerns that Professor John Fox expressed in our textbook.